This is a second take for a video that I took down thanks to David. He withdrew my attention that I confused between George Bidley, who is doing research about the ether, and James Bradley, who is doing research for stellar parallax and discovered the stellar aberration. Now, I took down the video, but in this second edition now, or second take, I didn't do any editing. So whenever you see this tilted telescope, you know I'm talking about George Bidley Airy, and whenever you see something else, you know I'm talking about James Bradley. Now let's start with the video. Hello everyone. I'm so glad to make this video about this amazing man, James Bradley Airy, and the video title is Airy's Success. And this brings to mind the phrase of Airy's failure. I don't know why they call it failure, but anyway, it's been said that his experiment with telescope filled with water failed to prove that there is something that is called ether, and I don't think that is a failure. But anyway, here is my analysis, which could be wrong because I'm not sure what exactly light is, and I didn't do proper research for that. So if you did the proper research, you can correct me and you can guide me for why Airy or James Bradley didn't get the results he expects when he did his water telescope observation or experiment. So let's assume that this black circle is a bullet, spherical in shape. I don't want it to be aerodynamic or having a specific shape, just a ball, and it's shot downward while there's a tube moving from left to right. And let's say the first portion of the tube is filled with say styrofoam, then maybe here cork, paper and wood. The bullet speed now has a relative speed and direction this way, and the change of speed will happen in both components, the vertical and the horizontal. But that's of course for bullets and materials. For light, I'm not sure, and because light is a very tricky issue. When you work with light, sometimes you have to deal with relativity, and I'm not also so familiar with relativity. Now that being said, let's move to Airy's success. So Airy's or James Bradley made some observations. He was seeking answers for the uncertainty as to whether stellar parallax exists or has effect or not. It's a long paragraph, I will not read it all. So his idea was to make observations to a certain star along the year and see how the direction of that star changes. I think I have to correct myself on this term, direction, because the change they observe is always in the elevation angle of the star, because you have two axes, the elevation axis and the right ascension, and I'll go to this right ascension. Right ascension depends on time, so it's very tricky to observe variations in right ascensions. So the variations he was looking for was in the elevation angle of the star. So he picked a star called I think Omega Draconis, and what he noticed that the elevation angle changed by 40 seconds between September and March. And at the same time, he was observing another star called Camelo. I'll call it Camelo. That's not the name. It's 35 in the constellation of Camelo, but I'll just call it for simplicity the star Camelo. Now his observation for that star came nearly. Well, first of all, the star is right ascension nearly exactly opposite to that of Omega Draconis. The variation is, or the variation in the elevation angle was 19 seconds. Now, before going any further into analyzing his results, let's have a little look at his experiment and the setting of his experiment. So he picked two stars, the Draconis and the Camelot, and each of those stars is at elevation angle of around 51 degrees, 51.5 to be close to exact. And he picked those elevation angles to have those stars vertical on his location, so that on the zenith the elevation angle of these stars is 90 degrees, and the elevation angle of the stars is only one direction, and the other direction is called the right ascension. Right ascension is always measured from the 21st of March. So, for example, Camelot right ascension is 6 hours on the 21st of March. This means that due to Earth rotation, when you're here, you see the sun. This is the sunrise, and 6 hours later, you see Camelot. So that's the right ascension for Camelot. Now, when you're here, you see the sunrise. Here is 6 hours. Here's another 6. That's 12. And here's another 6. That's 18 hours. That's when Draconis is on sunrise. So as you see on March 21st, he could see the two stars. One star he see around sunset, and the other see during sunrise. Next to that, what really happened, he was looking for stellar parallax, but something else he ran into is this stellar aberration. And if we are the sun, this is the sun point of view on March 21st. I think you can see that this picture is tilted, not like this one. This is the equator, but from the point of view of the sun on 21st of March, the equator is tilted this way, and so the whole setting is tilted to the right. So this is the movement of the Earth in relation to the sun. This movement is around 30 kilometers per second. So if you're here, just for simplicity, and you're moving this way, so you get the light from a different angle. You'll see the star from this angle, not from this angle. And 6 months later, you'll see the star from this angle, not this one. But during summer and winter, you will see the star exactly where it is supposed to be. That's for Draconis. You see the shift. Now here I put the same scale of this orange and red arrows to see the effect when the star is closer to the orbital plane from the point of view of the observer. Now you can see the shift is much less than this one. Until now, until this moment of explaining, This is thus just hypothesis. So we had to make some check to make sure that this hypothesis is correct. We have the speed of light, which is, let's say, 300,000 kilometers per second, and we had the speed of the Earth, which is 30 kilometers per second, and we have this angle and this angle. So I took this triangle out just to make it easy to do our calculations to confirm the results. This angle is 75 degrees. This 75 degrees is, let's go back here. It's the angle of the Earth tilt, that's 23.5, and then the elevation angle of the star without any variation, that's 51.5. So that's where I got the 75. So this angle is 15. We have the light speed, and we have this O, let's call it the orbital speed, and we have this x. This x is the horizontal component of the light speed according to this angle. So the light speed here should be a little bit less than 300,000 kilometers. I used this number, I didn't use the reduced number, but anyway, when we put relativity into these stuff, it will change all my calculations, but with a very tiny fraction, so I'm not worried about it. So anyway, this is the x component, and the x component is 300,000 by 1015, and it came to be like this: 80,384 kilometers per second, and the O, the orbital speed, is 30 kilometers per second. So the new x, this one, this is the new x here, will be 80,354. So we have distance here, and we have distance here. So the angle, we can calculate it, and it came like this. So this is where we see that almost 20 seconds less than 15 degrees. Of course, this drawing is not to scale. So let's go over this. Yeah, so he plotted the two stars elevation angle along 1 year, and this was the results. And this is what surprised him. He expected to see the exact opposite curve for both stars, and this results make him think that there's something more than stellar parallax, or that what he's observing is not stellar parallax. So I based some calculations, but of course more accurately, on a spreadsheet here. So this spreadsheet is originally my Sun calc, but I needed it for accurate determination of the angle between the Sun and the Earth. So anyway, I put the date 21st of March, and here is, oh sorry, this one, yeah, this one. So the right ascension for which star are we going to look at? Let's go for Draconis first. So this is Gamma Draconis. So the right ascension is 17 hour 56 minutes. So we can call that 18. Here 18. and the star latitude or elevation declination is 51 almost 0.5 51.5. So there is the 19 or almost 20. So if we say this number multiplied by 2, because the variation is in both directions, so this is the almost 40 seconds that he observed. The variation he observed 40 seconds. So now let's go to the other star, Camelo. In Camelo, right ascension is 6, and the elevation angle is also almost 51.5. So we'll just change the right ascension into 6, and there is the 90 seconds total variation. And as you see, it's opposite direction. But I wasn't satisfied with that. I wanted more, so I made a graph. So let's put the first star latitude 51.5, and right ascension say 6. When we say 6, I think that's which one of them is 6? Yeah, this is Camelo. So now we're looking at Camelo. Where is Camelo? The red one. This is Camelo, and you can see it's almost the same, except for my spots or my plots here is based on 7 days intervals. Of course, he couldn't, or maybe he did with different intervals. Now let's go for Draconis. The elevation angle is the same. The right ascension is 18, and here is Draconis. Let's compare it with his observation. Here is Draconis. So he gave us the solid ground to confirm that the light speed is indeed 300,000 kilometers per second, and that the orbital speed of the Earth is around 30 kilometers per second. And what I really like is this. These results were completely unexpected and inexplicable by existing theories. At that time, these observations, no one could explain it. So there's no tendency for bias. I'll put the file into the description. This file also contains the spreadsheet file. It contains my sun calc application with its equation for you if you want to check, and the ANALMA plotting graph or sheet. So I hope this was useful, and thanks all for watching. I know this was a little bit long, but it should have been done this way. Thank you for watching.